Do you hear me? Yeah, okay, right. Okay, so real-time collaboration. So I'll start with this question. Why do single applications still exist? So a single application is an application where only one user can work at the same time, can edit the document at the same time. So think about it. The first idea of real-time collaboration is very old. Here you can see Douglas Engelbart that envisioned real-time collaboration through a text document in 1968. The first successful product is 10 years old. It was Writely that have been bought by Google later to become Google Documents that you probably know. That product has a lot of competitors, such as web-based competitors, but also freeware competitors, and giant competitors with Microsoft, of course. And this product took a lot of market share in the enormous Office suite market, 20 billions. So that's the second point. The third point is that industries are going in that direction. So here you can see very famous and big companies with Adobe Anywhere, for example. They all have their program in order to reach the collaboration and sometimes real-time collaboration here in 3D. And the fourth point, which is to me the most important one, is that there is no disadvantage for the end user. I mean, if you want to work alone with a multi-user application, you can. If you want to or have to work offline, you also can. But if you want to invite a mate, a colleague within a document in order that he will help you on some part, then you can. And as we will see later, it brings many other advantages. So let me summarize. The first idea is very old. The first successful product is 10 years old. Industries are going in that direction, and there is no disadvantage for end users. So why do single-user applications still exist? That will be the underlying question of this conference, and we also see why it is currently changing. So I'd like to start by presenting ourselves, even if Jean-Jacques began that. And so you understand why we spent the 10 last years by studying this problem. So after graduating our engineering school, we were a bunch of development lovers that wanted to create some good music software, and especially a digital audio workstation, which is a kind of Photoshop, but for musicians. And we started cautiously with much simpler products, such as some effects, you can see here, or some instruments. And it was quite successful. And as a result, we had many famous musicians here, you can see, that used our product and that enjoyed to do so. So after that, we were prepared to the big project. We started to work on Home Studio. So Home Studio is a digital audio workstation where the users can record themselves, audio or MIDI. They can add some plugin, external plugins. So that's a quite complex application. That's 2 million lines of code. I don't know if there are some developers probably here. That means something. So that's an application that is complex, probably not in the size, but in the complexity, probably as complex as the application you do here. And the most specific feature of this application is the real-time collaboration. So here you can see 2 computers with 2 users. You have to imagine that, for example, the left one is in Paris, the other one is in New York. And the 2 users can work together for making a complete song. So one can record the drum, while the other one records the vocal and the guitar. And a third could come to mix the whole music. So that really makes sense for music, because every musician needs the skills of other musicians in order to make a complete project, a complete song. So that's why we work on this. So we released the Home Studio 3 years ago. So we had 130,000 users. So we also study the outcomes of real-time collaboration to our users. And yeah, that was a great experience. But when we started this project, we had no solution in order to handle the real-time collaboration problem, the technical part. So we had to create our own library in order to do so. And after 8 years and as many redesigns, complete rewrites, we had a quite good experience, and we realized that it was probably the first turnkey solution for complex application in order to add the real-time collaboration feature. So that's why we created Irisate, in order to bring real-time collaboration not only to musicians, but to every users of every industries. So yeah, we want to share our experience about real-time collaboration and also distribute our library that is called Flip. I'd like to start with the definition, because today real-time collaboration is more a marketing term than a technical one, even if it looks a bit technical, real-time. So our definition is based mostly on the most successful product, which is Google Doc, and there are 3 points. The first is that users can access the same document at the same time. And here, the tricky point is that it has to be the same document. So for example, if you're on Dropbox, you have a Dropbox folder, you share it, there is a document within it, and then 2 users are editing the document within the same folder Dropbox, then it's not real-time collaboration because they both have their version of the file. So you have 2 files, and then later you have to merge that. Second point is about undo-redo. So you have to have one undo-redo stack per user. So it may look a bit obvious, but we already tested some solution where the users, all action users are put together. So let's take the example, very basic, that I create an object, then I think about it 5 seconds, and then I destroy it. Then if during that 5 seconds another user just made some other action, when I undo, then I will destroy his action instead of mine. So, so clearly that's not what you want to do. You want some feature in order to allow the users to undo some other user's action, but that's not the way you want to do it. So clearly, one undo-redo stack per user. And the third point, the last point, is about the synchronization time. So the synchronization time is the time between when I do an action and when it is replicated to the other user's document. And that time should be as low as possible. We think a good goal should be under 1 second, and it's clearly feasible. There are 2 reasons for that. The first is about user experience. For example, 2 users can work and be over Skype, for example, conferencing, and they need to see the same document when they are talking about it. Otherwise, it would be not comfortable. And the second point is that you want to keep it as low as possible because of conflict. The longer your synchronization time is, and the more chance you will have to have conflicts, and the bigger your conflict will be. Let's take an example with Microsoft Excel, where the users have to do an action in order to synchronize their document. Then let's say they think about doing it every hour. Then during 1 hour, they will work on a part of the document, probably the same part. And then after that, the chance that a conflict happens will be huge, and the conflict will be enormous. For example, you can work on a line during 1 hour, and then at the end, maybe another user has destroyed this line, and then you have lost your whole work. So as you can see, your problem about conflicts are not growing linearly, but exponentially with your synchronization time. So you have to keep it low, and that should be, we think, under 1 second on your requirement list. That's it. Just to memorize, users can access the same documents at the same time. When they do, reduce tag per user, and synchronization time as low as possible. Okay, so now let's see what's coming next. So during the first part, I will talk about advantages that we've measured amongst our users, and also the design issues, the problems that are very specific to real-time collaboration that you have to handle when you are making a real-time collaboration application. And in the second part, Raphael will talk about how the magic happened and what is the development history about real-time collaboration. So let's start with the good side. Advantages. The first advantage is about document uniqueness. So real-time collaboration brings to your user document uniqueness. Let's see it with an example. That's the last contract we made with Irisate. And you see the first version are on the bottom. And then each time an executive or a lawyer edits the document and he had his name, then we reached the version 2. And then later we were very upset because it was too long. There was a final. We thought it was the final, but no, there was a final V2. So V2 final, V2B. And that was it. That was the final one. And the important thing here is that we made some error because two lawyers made some mistake when they merged the document manually. So that's clearly error prone to go that way. And that's what document uniqueness is about. So to me, there are two ways to reach document uniqueness. The first is that you put it on a server and you have a kind of lock mechanism. So the problem is that you lose a lot of productivity here, obviously, because only one user can edit the documents. And you also have the problem that sometimes a user will not release the document, so every other users are blocked. And so the second way to do it is the real-time collaboration, which have no downsides. Every user can edit it, and that's it. Okay, the second one, I will try to let you guess. You have to participate. So we asked to our users, so that's in music, as you could see, what was the main advantage that have brought the real-time collaboration through Home Studio. So four possibilities: productivity, learning, quality, and reducing costs. So reducing costs is about the fact that for our users, they have not to, for example, rent a rehearsal room or rent a studio, or for more professional to avoid to buy a plane ticket in order to make a take, for example. So who think they answer productivity? Okay, who thinks they answer learning? Yeah, who thinks they answer quality? Okay, and who think they answer reducing costs? Okay, oh, so more on quality. And surprisingly, they answered learning curve. And one of the core user, very experienced user, told us that during the last year, he learned more within Home Studio than the 10 years before. And the reason of that is that when you're using an application simultaneously with another user, then sometimes he's just making an action that you don't know, and you just can ask him, how did you do that? For example, a shortcut that it's clearly more efficient. Or why did you put the volume to minus 3.4 dB? And then it will teach you some production, how to produce sound. And yeah, so basically, anytime you can say, how did you do that? And then you learn a lot because of that. And another strong indication of this is that many universities contact us in order to create some pilot program, because the teachers have seen the opportunity to make some, for example, group of students. They can make group of students in order to realize a project, and then the teacher can enter anytime in the project and make some comments or just give some advice or yeah. So that's interactive, and that's a great new way to work in universities. The third advantage. So I put together productivity, quality, costs. The reason is that if you increase your productivity, so clearly you will decrease your costs, and then you have more money to invest on the quality. So clearly all these are linked. But I will detail each of one. So about productivity, the main advantage is that your user or worker can work in a parallel mode. So that's the way you increase your productivity. And I have a story about that. A friend of mine is one of the lead developer in Call of Duty, probably you know, a first-person shooter. And he told me that during the process, when they work on a level, they had to schedule very precisely during 2 months each time they edit the level. So for example, during from 8 a.m. to 11 a.m., Frank have to work on the lightning, and then from 11 to 2 p.m., Raphael has to work on the shaders, and so on during 2 months. And each time they want to edit against the level, there is a 2 months scheduling. So you can clearly see in that example how much more productive it would be if they were able to work together on the same project. About quality, it's about that you are able to reach any talent on the whole planet. So for example, in Home Studio, at some time, a mandolin player joined the community, and that was a great opportunity for every musician to be able to ask for the mandolin player to make some text, because that's a bit rare to have a mandolin player, and then every users were able to invite him and ask him to replace a guitar with a mandolin, for example. And that was great. It reached a lot to our users. About cost, it's mainly because you will be able, for example, to outsource a part of your team. So it depends on the industries, but clearly in music that was not really the case, but in other industries that's a strong vector. The fourth advantage, you may ask why, but is green. So the relation between real-time collaboration and environment is that it really eases a lot the remote working. And sometimes it just makes the remote working possible. And we have a lot of studies about remote working. This is the first, it's on USA, so on the USA territory. If every worker had the opportunity to work at home 1 day per week, then it would save 3.2 billion gas liters every year. So that's a strong and huge leverage. Another number is coming from Sun Microsystem, where they estimate that 98% of their employee footprints come from their travel from work to home. So now, the downside, not really, but the design issues that are very specific to real-time collaboration. So I'll start. The first one is mainly how you handle the conflicts. So that's the first we think about. And here you will see Play Canvas, which is probably the most advanced game engine that is real-time collaborative. And the example here is very simple, where 2 users will try to move the tree at the same time. So here you can see the tree is a bit blinking, and then the left user have won. For the other one, too bad. So you can see technically it's okay, because at the end they see the same thing, so that's great. But to me, there are 3 problems. The first is that they have no chance to know than that another user was selecting or using the same object. So they cannot forecast that a conflict may happen. The second problem is about the blinking. You have to keep in mind that a user will only see his screen, so that would be very strange to have the tree blinking while you are shifting it. So yeah, it looks buggy. And the third problem is that the right user that has lost the conflict had no notification at all. So he made an action and nothing happened and I don't know why. So this is how we handled this within Home Studio. I'll show you. So that's the same very simple example where two users try to move a pattern on the timeline. So there are three differences. The first is at the beginning, we play an animation to show to the users that two users are selecting the same object. So we use a yellow to orange blinking animation in order to signify them this information. Then we use what we call, I think, the ghost or ghost shifting, I don't know, which is the idea that when a user moves an object, we keep the initial position and we apply the shifting only at the release of the action. So when the user releases the mouse button, for example. So in that way, the object does not blink because we apply only at the end. And finally, the users that have lost the conflict, which is this time the left one, has a red animation. So I will probably play it again so you will see the 3 points. Here we have a yellow to orange animation, then the ghost shifting, and then the red one animation, the left user pattern. So we're happy with that. And probably you may think, okay, but you are synchronizing everything very quickly, so this kind of conflict will happen very rarely, and that's true. But that's probably the first thing that your users will test. So that's important to build some confidence very at the early point between your application and your users. Design problem number 2, about selection and view. So we've just talked about selection, and here the use case is that two users are working together and one user will try to explain to the other one a problem on the project. So they want to have this feature, which is great in Play Canvas, where you can share a camera between two users. So they are sure that see exactly the same thing. We have the same feature in Home Studio, but here you can see the same problem in another way, that I will struggle to explain to my colleague what trees I want to show. So for example, if there is a problem on this tree, I won't be able to show him because of the lack of selection sharing. And then when you introduce the selection, when you show the other user selection, you have a new problem, which is how can you differentiate other user selection from yours and every selection. So here our Google Doc did, or do. So here you can see that it is a very good solution where they use a color for one user, another color for the other user. When the user moves his selection, the cursor, you have the name of the user, so that's really great. And I don't think they can improve this. I think that's great. But if you have an application where you already use a color to signify something to your users, probably you don't want to add a rainbow in your user interface. And that was the problem for Home Studio, because we already use the color for coloring the tracks, so that the user can say, okay, in red, all the red tracks will be for the drum, the blue one will be for the guitar, and so on. So we really needed to keep the colors for something else. So the way we did it is that we just took two colors. One color is for me, for the user that is using the application, and another color is for the other users. So the yellow is for the user working, and the orange is for all other users, so that you only have two colors, and that's it. So that's how we did. And we are happy with that because we have some other feature in order, if you want to know who did what, we'll see later, but we have other feature to reach this information. Third problem, undo, redo, relative or absolute. So here an example to show that is that the left user will move just one tree in order to reach a kind of triangle forest. Then the other user will move the whole forest. Here, the triangle form. Then the other user move the four trees. And then the first user undo his action. And probably that's not what you want to have when you're the first user, because you probably just want to go in the square form of the forest. And then you have just nothing, you have a new form of forest, which is probably not the one you want. So probably it's more interesting in 3D, in a 3D environment, to have a kind of relative undo, and to handle the shifting in a relative mode. So here, that's almost the same. So we have a chord, so clearly it makes sense for a musician. If you change one note, the frequency of one note, clearly that's not the same chord. And here, a user will just move a note in time, just to make more humanized maybe, and then the other user move the chord one octave upper. And here we see that when the first user undo his action, we keep the chord at his original way. So that's a relative move instead of an absolute one. If we had made an absolute, then the note would have been one octave below. Okay, so the fourth problem, who did what? So that's a problem you already have in a single user application, but that's a bit more for real-time collaborative one. The reason of that is sometimes you want to be able to ask who did that, because a user, for example, you have 4 people that handle the shaders, and then you have a problem with the shader, and you want to be able to see who did that shader, so that I will ask him to change something on that. So that's really important, and you have to put it if you have that kind of feature. So here how Microsoft do that, and that's a great way. You can see every change. You can also put comments, and it appears on a column, and you also see which object has been destroyed. That's great, but that's very specific to a flat model. If you have something that is more like a tree, then you probably have no solution like that. So the way we did that is very simple. Every object in Home Studio has an attribute, which is the maker, the author. And then we add some features. Here you can see in the inspector, the author. And we add some feature where you can select, for example, every object that has been made by the one user. You can select every tracks that have been made by one user, every pattern, and so on. So that's really handy. Problem number 5, misunderstanding alteration. So here probably the author of the path is not the same as the author of the fence. And the idea here is that when you are working together on the same project, you will have more error because the users don't have in mind the whole project. And if they did the project alone, clearly they have in mind the whole project. But there, that's not the case. So sometimes a user will move some part or change some part of the document, and he won't realize that he was destroying something. So you need a feature to give the opportunity to your users to retrieve some part of their work. So how Google did that, that's very standard now. That's a revision history that every developer knows, but very well done here in Google Doc. You can go back in time, so the server makes some save every 10 minutes, I think, or something like that. Then you can select a version, copy a block, then go on your trunk or your last revision and paste it. So very good solution. And we did exactly the same with GNOME Studio. We just add one feature, which is we give the opportunity to a user to make their own snapshots. We call that snapshot. The use case that is behind that is that sometimes a user wants to try something. So he wants to save the document at this state, and then try, for example, replace the guitar by the mandolin. And then he will work on that during one day. And when you want to go back in time, because he's not happy with this, then if you have a list of timestamps, it's a bit confusing. So now when he go back in time, he just see his snapshot with his name, and we put a nice picture, so that's easy to memorize and to go back to it. Yeah, the thing I did not say about the last one is that we think that you cannot release a real-time collaborative version of a product without this kind of time machine, because else your user will complain a lot. And we think that's mandatory. Problem number 6. I will show you, so move versus destroy. So here a video, you see the house just disappear. A second video with the house disappearing again. So you may think that's the same thing, right? But let's see the full video. The first case, another user moved the house. And in the second case, the other user deleted the house. And clearly you want the other user to understand that. You have to find a way to signify to your user that there were a difference between a shifting and a deletion. So how we did that? Very simple. So that's the same. Here you can see a shifting. And here, for the deletion, we just play an animation. We play a kind of flip animation. And then the user, when they know the interface of Home Studio, when they are a bit experienced, they know that each time that is this animation, that's a deletion. And if they don't, that was a shifting, probably. And probably in a 3D environment, there is another aspect, which is a kind of invisibility. When you make an object invisible, then probably you have to find another animation to signify that. I don't know. So that's it. Problem number 7. Disabling shared or not. So generally, when you're working on the design of an application and the real-time collaborative part, it's very easy to know if you want a data to be shared or not. For example, audio or MIDI is shared in Home Studio because that's just our raison d'être. So clearly we'll share that. But about the playhead, for example, it's really also obvious that we won't share the playhead because, for example, I want to work on the first part of the project, on the intro, and another user will work on the outro. So clearly we need each one to have our own playhead. But sometimes, and especially for disabling, it's not obvious because for some use case, you want to have the disabling not shared, and that's the main use case. For example, in music, If I work on the drum, I want to mute every other tracks, probably, just to hear the drum. And then I don't want to share the mute, because else, otherwise, the other user won't be able to work on another part. But sometimes I also want to disable an object because I want to be able to retrieve it. But for now, for example, I made a new mandolin take, and I want to keep the guitar track, okay? Because maybe I will ask to my partners, maybe they will be happy with the mandolin, but maybe not. So I want to be able to put the guitar back easily. So that's another use case. And the way we did it, that's very small. I have to look on the left screen, but we put a button which is a mute, which is not shared, but the main one, and another one which is shared, and you can see that the mute is grayed. We gray the patterns, and so that the user can understand that, okay, I did that, that's now that it's grayed, so probably that's also great for the other users, and it works well. And it's used on every project. The 8th problem, so the last one, work in progress. So the idea here is that sometimes we're working on something and it's not the final version and we don't want to share it to the others. And when we are alone, that's not a problem because I will just send my email when it's done. But when we're working together, that's a problem. And especially, for example, for shy people that want to work their first takes, but also in a more professional way. Sometimes you don't want to share because it will just bother and reduce your productivity of the other users. So we did something in Home Studio which is quite unique. We haven't seen that in other applications, what we've called it private track. And that's a space that is not shared, where a user can work. So here the left user can work during days on a track. And when he's happy about his work, then he can just put it on a normal track. And then it's shared. And that's a great way. And we introduced that during the beta period of our product. And today it's used on every big project. Each time there are many people working on the same project, they all use the private track in order to work after, just before sharing it. Okay, so that's it for my part. I will come back later to answer my initial question, but here now I give the floor to Raphael, who will talk about the development part.
Hi everyone, my name is Raphael Dinger. My team and I made Flips, the real-time collaboration engine behind Home Studio. So the goal of this talk for me is to show you the evolution of real-time collaboration over the years and to give you an understanding of the technical challenge and intuition about them. So first, we need to start with what is a real-time collaboration from a design, from a user experience point of view. So what is it? So we've seen this a bit earlier, but this is this idea of we have like multiple users working on the same document at the same time. But first, you need to have a single user application, the same features as for the single user application. And then only you will add additional features for real-time communication. Okay? So how are we going to do that? So here, from a technical point of view, we are going to see the problem modelization. So how does it look like? It's one model, and it's actually quite good. So we are going to say that the model needs to meet like those 3 properties, and we are going to see each of them after. So there is convergence, user intention preservation, and finally, causality preservation. So what is convergence? Let's say that we have 2 users, user 1 and user 2, and they start with some text, a piece of text with just A, B, C. Then let's say that user 1 is inserting an x before A, okay, and user 2 is inserting a y between B and C. Convergence is going to express that if they stop editing their documents, at some point of time, they will reach the same document state, okay? So this is convergence. Now, what is user intention preservation? So let's take another user and the same piece of text ABC. And let's say again that this user wants to put a y between B and C. User intention is going to express that after some edits, his initial intent here for y to be B and C is preserved. On the left side, for example, we can see that the y disappeared. The user intention was lost, okay? And on the right side, the y is here, but it is not between B and C. User intention was lost. Finally, to express causality preservation, we are going to look at 3 users. So let's say that user 1 is asking the question, hey, how are you? Then user 2 is seeing the question and is replying, I'm good. If user 3 first see I'm good before the question, we don't preserve causality. He first needs to see the question before he sees the answer. This is how you express causality preservation. So this is a way to model the problem, and then now we obviously have problem constraints. The first problem we have is that we want a reactive user interface. Okay, so what does it mean? It means that if I edit the documents, I probably don't want to wait for 1 second before seeing actually the result of my edits. I want it to be reactive. And typically, we want this to happen around or less than 100 milliseconds. And then we have a physical constraint, which is speed of light, meaning that for information to flow back and forth from two opposite locations in the world, this is going to take 200 milliseconds. This is an idea, okay? So we see that we want a reactive user interface around or less than 100 milliseconds. And at the same time, the time for information to flow back and forth is going to take something like 200 milliseconds. So we've got like some kind of problem. So this problem is not new, obviously, and there is solution for that, which are typically optimistic replication. And we want this to happen concurrently. So what is optimistic replication? This is the idea of having a local replica, a local copy of your documents. In this case, this means that when you are going to make an edit, you are going to apply it directly onto your local version of the document, okay? So that the edit can be almost instantaneous. And then after, you are going to send the changes to the other people on the network. So, and for the concurrence, the idea is the following. So here I'm showing how locking looks like. So for example, we can consider 2 users. User 1 and user 2 want to edit the document, but they are using locking. So this means that if user 2 wants to edit the document, he will need to wait for user 1 to unlock it. Okay, this is not what we want. What we want is not to have lock, so that it can edit the document at the same time. And if you think about it, this is quite very similar to the way, I guess there is a lot of developer here, that we use system threads, where there was like old techniques, like mutex, for example, and we are all going into favor of compare and swap techniques, typically lock-free architecture. Lock-free architecture has a future, and we need to use less and less mutex. This is exactly some of the same idea. So, to start, we are going to see some kind of historical solution, which is called operational transformation, OT in short. So let me describe it to you. So first, we are going to see like what it takes to somehow understand it. So let's start again with user 1 and user 2 having the same piece of text with ABC. And user 1 wants to insert an X before A, and user 2 wants to insert a Y between B and C. With operational transformation, we are going to encode this information the following way. For the user 1 is going to put an X before position 0, And for user 2, she is going to put a y at before position 2, okay? So if we apply, let's say, this kind of algorithm naively, where we just apply those two operations on each of the sites, what we are going to have is that we will have not the same document state on each side. So this means that we don't have convergence. The pieces of text are different, okay, on both sides. But also, we can see on the left that the y is not between B and C. So we also lost user intention, okay? So we might think that it's because actually we somehow change the order of execution of things, of operations. So maybe we could timestamp them using, for example, a vector clock algorithm, just to make sure that they are executed in the same order. And in this case, because we start with the same state and we apply the same operation in the same order, we are going to have convergence because there is the same text on both sides. But again, we can see that on the right, a y is not between B and C. So we've lost user intention again. So what does operational transformation is the idea to actually transform operation to take into account the context of execution of operation. So on the left, we can see that because we've inserted an x before position 0, it's going to shift the whole string. So the idea is to transform the operation on the left to take into account the shift by one letter and then transform position 2 to position 3. And in this case, we have convergence because the text is the same on both sides, and we also had user intention. We also preserve user intention. So, looks nice, right? But here we just considered two concurrent inserts. So, but we would need to also to consider insert and delete, delete and insert, delete and delete. And this would be very simple, just for text, something very simple. But in the case, for example, of Google Wave OT, they had 15 different operations, meaning more than 200 algorithms to design and to verify. So it's quite a lot of work. Then here, we only consider 2 users, but problems are really harder with more users. And even some solutions like OTA Explorers have been made to understand actually problems that could arise with more users when there are more than 2. So it's really complex. But that's not all. So for OT alone, you have 16 different algorithms with different trade-offs. And if it was still not all, sometimes you've got publication disproving other publications. So we can see it's a very complex problem. This solution is really quite complex. So I'm going to quote Joseph Gentle, who has been working on the Google Wave OT platform, and he says this: unfortunately, implementing OT sucks. There is 1 million algorithms with different trade-offs. The algorithms are really hard and time-consuming to implement correctly. Wave took 2 years to write, and if we rewrote it today, it would take almost as long to write a second time. So you can see, and he really knows things about operational transformation. But, so yeah, we can see OT doesn't really solve problem really easily. It's really, really complex. But it's not the only solution. We've got more solutions. So let's take a look at other solutions. And we will start with different patch, which seems really nice idea, even in the end it's not actually so great. So it comes from Niall Fraser, with a Google engineer. And I'm just showing you actually this example because even if it's not necessarily like the best one, I think Niall had a really crucial understanding of operational transformation problem. And we are going to see this like very quickly. So the idea is quite easy to understand. It's really a similar concept like what tools we use daily as developers like Git or SVN. So what does it look like? We have our current document on which we are making edits. But the system actually still have in memory a previous version of the documents. You know, it's like the last version we've pushed on the servers. It's called the shadow documents. And we have the current document when we've just made our edits. Then, using a diff tool, we are going to make the difference between those two edits to make a patch out of it. This is the idea. And this patch is going to be sent to other people on the network, and it's going to be applied on other remote sites. Okay? And the really interesting idea, we are going to see it like right now. So let's consider that a user is starting with this sentence. The cat is nice. My cat is very nice. And then he wants to change it to the cat is mean. Okay? So we can, for example, use the diff we typically have in our tools, which are usually trying to make minimal patch. Okay? So here, if we look at it, what is it going to do? It's going to remove NIC because it detected that actually those three letters are not here anymore. Then it's going to keep the E, and then it's going to add AIM, okay? But somehow it's hard to understand, like for humans, when we see that, we need to think a little bit to see, oh yes, that's right, this is the way it is. So this is for a minimal patch. But already, if you take a word patch, or a semantic patch, here it's a word patch, then in this case, you can see that we transform nice to mean, and we keep the user intention. The user intention was to change the word nice to mean. And here, this is preserved, okay? And this is where it's really good, this kind of approach, and the crucial understanding about it is that in our first example with operational transformation, we had this thing where we say insert Y before position 2, but we lose the concept of between B and C, and this is really important. So the problem with operational transformation is that it's index-based, and here with a patch, it's context-based. It keeps this information between B and C. So it really captures user intention. Okay? Right for everyone? Yes? Good. So let's get to the real stuff. So let's start with CRDT, which stands for conflict-free replicated data types, and which have been developed by INRIA. So the first observation of CRDT is to try to understand, okay, what is so problematic with operational transformation? And the problem of operational transformation is actually to transform operation. It's too complex. Transforming is complex, and the control flow is also very complex. So they start with this idea about we won't have any kind of operational transformation first. Then we are going to simplify the control flow by saying that we can apply operations in any order. Okay? And finally, to make self-thing control flow really easier, there will be no arbitration, and we are going to do this with no conflict. So how can we do that? It's through operation design. All those things are done through operation design. And all this is done, it's really kind of simple mathematically. It's saying that we want operation to be associative and commutative, okay? And we want them to be idempotent. So associativity and commutativity, I guess that everyone is fine with that. And maybe something new, it's quite more rare, idempotency, express the fact that if you apply an operation more than once, it will have the same effect that if you would apply it once. Very nice property. So associativity and commutativity is going to express the fact that we can execute operation in any order. And idempotency is here for fault tolerance. If there is a problem on the network, you can send a message twice, thrice. It will still have the same effect as just once. Really, those three properties. So let's take an example. So here you can recognize one way to express a plus operator. And we can clearly see, we know actually that it's associative and commutative, but it's not idempotent. There is only one case where y is 0. In this case, you can apply it more than once, it will have the same effect. But if y is 2, and if you apply it twice, well, then you will add 4, so it's not idempotent. So let's try to see if someone has an idea about how can we have those three properties with an operation. Anyone? No? No? No one? Okay, so we can use max, okay? Max is going to be associative and commutative, and it's also going to be idempotent. Is that clear to everyone? Yes? Yeah? Good. So this operation is really interesting because if you read CRDT papers, it's always coming back and back. So if it's not a max, and if we are handling set, it's going to be onions, but this is always the same idea somehow. So let's take a more detailed look about CRDT. So CRDT defines 3 methods. The first one is query, okay? It's about reading the value, we are considering a value, and it's reading a value through your local replica of the document, okay? Update is going to be your write operation. This is where you are going to modify your operation, okay? But you only do it just locally, okay? Then merge is this operation to integrate actually the changes and the different document state and merge them into your document. Is it okay for everyone? Yes? So we are going to take the example of a counter. So this is going to be like a Facebook like or a YouTube like. We've just to start this idea of you can only increment the like. You cannot decrement it. So to show you the algorithm, it's quite simple. It's very similar to the vector clock algorithm for people that know it. So we are going to consider a vector of size n, where n is going to be your cluster size. Usually CRDT is used server side, so you have the infrastructure and you have a certain number fixed of servers, okay? And we start by initiating this vector with just 0 everywhere. And S is this vector and it represents the state, okay? So to handle concurrency, the idea, and I guess you all know it, is to make sure that no actually two computers or system are going to write at the same location. So here the idea to make concurrency happen is to make sure that node with index I is going to write at index I into the vector. In this case, we know that just one node can actually write at this position. So this is how we are going to handle concurrency. Then, when we want to update, the thing is the node is going to increment the value at the position into the vector. And if we want to know the total number of likes through all the nodes, we are just going to sum the vector component to component to get the final number of likes. Okay? Is it okay for everyone right now? Yeah? Okay, and then when we merge, so this is where within this max operation, we are going to get the other servers actually message, and they are actually on state, and we are going to merge it into our on state by maxing component by component, okay? Servers are going to broadcast their states actually to every neighboring servers on the cluster, and they are going to, the remote server is going to get it and merge it into its local state. So this is how we can do that. And this max operation has this associativity, commutativity, and idempotent properties. So this is where actually all the magic happens. So now let's consider a p-n counter, meaning that we can increment, but we can also decrement actually the value, okay? And here my goal is to give you an understanding of the operation design. What does it take to make a CRDT operation? And so, to take it quickly, the idea is always to look into the future, never roll back. There is no rollback in CRDT. So for example, in our previous example, if we were, let's say, incrementing a value and then decrementing it, most probably we are going actually to reach a state that we had already before. So it's not going to work. So we are saying that the system is monotonically increasing in state, meaning that we always need to look forward and make always a state that always grows. So how can we do that? As someone has an idea about it? Still no? Come on. So we are going to use two vectors. One is going, same idea as before. One is going to represent positive numbers, and the other one is going to represent negative numbers, meaning that we are always going to increase actually values, but we are going to separate between the time when you actually like and the time where you actually unlike. And then after that, well, it's all really simple. So for the update part, if we like, we are going to increment the positive vector, and if we unlike, we are going to increase the negative vector, okay? then query expressed very simply by just making the difference between those two vectors, okay, so by summing every component. And finally, merge, same idea, we are just maxing, but making it separate for each vector. This is how it works, okay? But it's really, really nice because we have no control flow. We have no conflict. We have no arbitration. It's very robust. When you've met all the properties, you know that it's done, basically. And you don't have any kind of control flow algorithm. But as we can see, we only made like a contour that you could increment and decrement, okay? It's supposed to be very simple, but already the operation is really hard to design, okay? It's so hard that researchers for CRDD are making operations portfolio, okay? So usually when you think like, oh, I need this, then you are going to look at the last academic papers that make like a summary of the latest discovery of operations that are CRDT compatible. So this is the idea behind it. The good news is that CRDD is used industrially. And I'm giving you here just one example, really important in my opinion, is the Bet365 website. It's an online betting website. It's got 2.5 million users. And it's really important because we know that everything which is about money, basically people are really serious about it. So it means like it's production ready for very important things. Okay? And it's not the only example, but probably one of the good ones. So let's now come to system invariance. System invariance is something we always have in our applications, the way we develop, like to make sure that on our data model we meet some constraints, okay? So here, let's say we have like, yes, a question? No, okay. That here we want to make sure, for example, that our contour, the number of like, is not going to be more than 1,000, okay? How do you do that with CRDD? You do it through operation design. So with this system invariant, these constraints, it's really easy to express in this way, actually. So we are just, in our max operation, going to max it also with 1,000 component by components. Actually, it's one. But yeah, this is the idea, okay? So, but if we take a system invariant, very simple one, expressing the constraint between two values A and B, and we say that, okay, we want A, B to be so that they are fitting on a disk of radius 1, okay? It's really kind of a very simple constraint, but already actually, how do you do that with CRDD? Is there any operation in the portfolio? Actually, there is not. So you would already need, for this very simple constraint, already start to do some research, which can be very long. So, and also, like, how do you do undo? There is no rollback. So how do you do that? So actually, the idea is about getting more, actually, things into the state to represent undo, because we always need to grow. And the general idea is to hide things. You hide things. You grow the state to hide some values. So for example, in our contour, if we wanted like to do like some kind of undo, we would need to mark like some bit to say that, okay, don't take into account this one. This is the idea behind it. And it's part of operation design. So CRDD has some limitations. So there is no rollback. It's really good because it makes this algorithm like so robust. But at the same time, it's quite hard to express really simple things like system invariance or, for example, undo. System invariants are built into operations. So it's just like every time a specification change and a system invariant change, you will need to redesign your operation, okay? And what happens if in your data model, you suddenly have system invariants across the model of two different values suddenly? It's quite complicated. So now let's take a look at Flip. And I will start with this quote from Hermann Hauser. He's the CEO from Acorn, and he was in charge of managing people who made the first version of the ARM chip, which are powering our iPhone or iPad. And he said this sentence: I took two crucial decisions about making this processor. I gave them no people, I gave them no money. There was no way for them to come up with a complex chip. And With Flip, when I look back, we had a very small staff, very, very small. And at the same time, Home Studio, as you can imagine, was a really big project. And we really need to be simple. And from my point of view, in my opinion, when I look back, I think it was really a crucial decision. So first, we had to look into that. All the solutions like CRD, the operations transformation, are made to be peer-to-peer, okay? But we all know here that distributed systems are harder to design than, for example, central systems, okay? And we had a competitor called Rocket Network. And Rocket Network made kind of a very simple real-time collaborative system, so it was not as good as solutions that exist now. But their problem, they just failed and they just shut down. Why? It was not so much about collaboration. It's just because they wanted like to make this peer-to-peer network, they had to make sure that people would actually configure their router for them like to accept actually packets, like getting in their network. So they had to configure their routers. And maybe it's okay when you've got like ITs in a company, but for people working alone, it's going to be a very complicated task. And just for that, actually, they failed. And if you want to know about like a practical, realistic implementation of peer-to-peer, you need to look on the Sky part with the supernodes. I don't know if some of you here know how it's done. It's using supernodes, which were not part of the infrastructure back in the days. And it's really quite complicated just to have a working solution of peer-to-peer. So and also you need to consider that you need to store documents somewhere, because most probably you will make some work, you will collaborate with someone which is probably not in the same time zone. And you want to make sure that everyone is working on the last version of the document. So you probably want to store them centrally. And even if you look at Google Docs has a central server to store the documents. So we came to the conclusion that peer-to-peer is quite actually expensive for probably not so much benefits, and we gain something very important, is that instead of having a partial ordering on events, like distributed systems, we have a total order of events. So it's changed mathematically everything to something much more simpler. So for Flip operation, what we discovered very quickly is that we want user intention to be more explicit. Then we want something conflict-free, but almost conflict-free. And here the important word is almost, as compared for CRDD, who is going to always make something conflict-free. And we had this intuition that maybe actually conflicting when user intentions conflict is totally okay. So to illustrate that, we are going to get into a world of developers. We manipulate data models. We usually handle data models with values and containers. And then let's take an example. Let's have an intuition about values. So let's say that we've got a star, and user 1 wants to put it at some position, while user 2 wanted like to put it at some other position, okay? Maybe it's totally fine to say that user 1 is going to fail to do it, or maybe user 2, maybe. And to continue on this intuition on how to do things, let's consider data models. So usually we start with user actions. And a way to represent user action can be done through transactions, okay? We are going to say like a user action is a transaction, okay? And this transaction is going to be made of atoms, and those atoms are going to be the tiniest parts that can actually modify a document over time, okay? And we've seen like from the very beginning that we want all this to be lock-free, okay? So if I show you atoms and lock-free, does someone has an intuition about how we can do things? Yes, no? Atomic instructions. The idea is to use the same concept as for compare and swap that you've got in Intel processors. So we are going to design operation with this concept. So one way to represent that, so I'm giving you here like a very simple way, like for values, is to say that for operation which is going to transition from A to B, to remind you like compare and swap is this idea of if it's the same as what I expect, then I will change it to another value. So here it's like to transition from A to B, what we are going to say is that we have a constant function which always return B. And what is probably non-standard is we are going to define it on a very small domain, which is going to be the single element of A. Meaning that this function, as you can only like have an input which is exactly A. Okay, so this is exactly one way actually like to represent compare and swap. Okay, so here's an important thing from the mathematical world to the programming world is that the execution is a domain. This is the idea behind it. So let's have a look at it. So let's say that the star we've seen before is at position 0. And the first user wants to move it from 0 to -1. And then the second user wants to move it from 0 to 2, okay? And because we have a total order of event, because we are on a central server, the operations are actually going to be executed in a specific order. So let's say that the second user actually gets its operation executed first. In this case, it's going to be able actually to apply this function because it's actually on the right domain. It starts from 0. The position of the star was 0, so we can execute or apply the function. And then the star is going to position 2. But when the second operation is going to come, we see we can't apply this function because the star position is at 2 and the operation domain is just like this single element 0. Okay? So this is the idea behind it. So let's now take, we've got like numbers of containers in Flip. Let's take a very simple one. Let's say a vector or a list, an ordered container. And so here I've represented like typically a vector starting at index 0, having 3 elements. And on the left and right side, I'm putting those virtual elements we use in our developer world to represent the first element, the virtual element before the first element, and then the virtual element after the last element to allow, for example, like to push back or these kind of things. So I'm showing you this, and this is the way actually, for example, operational transformation represents a piece of text. But if I show you this, for example, do you have an idea, do you have an intuition on how actually we can do something about collaboration and inserting things? Anyone has an idea? No one? Very shy, okay. We can just divide actually as many times as we want the space between 0 and 1. We are considering floating point numbers, so not necessarily floating point numbers like we have in processor, who are limited to 32 or let's say 64 bits, but more generally floating point numbers with no limitation of bits, so we can always actually divide and put an element between the other two. It's really important. And when we think, the solution actually is quite naive, right? But we are thinking also like, yeah, but we have only one character and one floating point number, which can be very big, just to encode like the position. So maybe it's kind of a waste of space, right? It is, but when you think about it, actually for an average book chapter, okay, like any kind of book, the size of those keys, like the floating point numbers, is going to represent 25 megabytes, okay? When Google Chrome is probably like taking half a gigabyte in the background. So maybe 25 megabytes is a waste somehow of space, but on today's computer, it's probably good enough, a good enough solution. So here we can also see that if two people, let's say like 0.25 is not here, two people are trying to insert an element between 0 and 0.5, it's going to conflict, right? So we can think about like, how can we make it here so that we can have less conflict? So does someone has an idea? No? Yes? No? Okay, so we can do it through randomness. This is another idea. So just to make sure that they are not going to collide, we are going to put some random bits. And in this case, actually, we have this very important property. So mathematically speaking, it's not conflict-free because you can get the same random numbers that's going to conflict. But most of the time, you can design your random algorithm and the number of random bits to make it so that a conflict is going to be very rare. So it's not strictly never happening, but it's going to be really, really rare, okay? So this is a way actually to handle conflicts in an ordered container. And this solution, actually, it's one which is used in Home Studio. It's really nice, like for small containers. So when you've got like a container of 1,000 or 10,000 elements, this is a very, very good solution, like for small containers. So if we need to remember something, is that those float index, they provide more context implicitly, because it's a position somewhere. You know, it's even if the two neighboring elements are disappearing, we still know actually where we are. So it's very, very powerful. And also an idea, a very, very strong idea, is that this float index is a unique identifier. You can refer it like some kind of address or something like that. It's a unique identifier of the underlying element. This is very, very strong. And finally, those algorithms are lock-free. It's because the idea of making a float index is the same as allocating, and we can, with randomness, actually make a lock-free allocator. So it's really, really strong. So let's take a look at transactions. So we've seen like one atomic operation, and here the idea is like just to make transaction, we are going to compose actually those functions. So actually, you can't always write actually this expression, because if the domain are not matching, actually this function is ill-formed, okay? But let's say for the illustration that we can write this expression. If we want to express the transaction inverse, it's going to be very simple. So first we are going to write actually the inverse of an operation. And for values that I've shown you before, actually it expresses very simply. The inverse for a transition from A to B, it's very intuitive, right? It's just going from B to A, okay? After that, you can prove it. But it's quite, the intuition is really strong on this one. And then to actually write a transaction inverse, you are just going to invert every operation and then compose them, but in the reverse order. It's simple as this. And so the idea after that is when we are applying actually the transaction, we don't calculate the function beforehand. This would be like on the computing side, not necessarily efficient. So to do that, actually we are going to try to execute every operation. And when we have a domain problem, we are just going like to stop. And the very good thing is in this case where, for example, operation 3 could not actually be executed. The idea is that we can still express very, very easily actually the inverse of operation. So we can just roll back actually where we were and get back exactly to the same document state where we were before. So we call this structural validation in the flip world, and then there is another validation we call logical validation, and it expresses system invariance. And the idea is that usually when we make an application, we need a lot of flexibility on system invariance because specification always change. So how does it look like? Let's suppose that every operation actually can be executed. In this case, we've got structural validation, okay? But still, because we have this operation and writing the inverse is like so easy, we can still actually roll back the transaction very, very easily. So even when it's completely to the new document state, we can still roll back very easily. So what is very great in Flip is that operation design is completely decorrelated from system invariance. We've seen that in CRDD, actually, it's really strongly correlated. But in Flip, it's completely decorrelated. So you build your operation design one and for all. Actually, it's already done. And then after that, you can write your system invariance freely. And the good thing is like control flow is totally handling it. You don't need to make some kind of magic because all those math behind are just making it really easy. And finally, if you think about it, inverting a transaction, we've seen that a user action, we model it like a transaction. So actually undoing something is somehow rollbacking this transaction. And we have a very simple way to express a transaction inverse. So here we have a very robust, elegant, and very, very easy way to express undo and redo. So something like to remember. Conflicting when users conflict was really kind of a very interesting idea. Also, we have more context. This is really important. More context and no operation transformation. And finally, a very flexible system invariant engine. So, to get to a summary, First, I will say, if you need to remember something, be very cautious with operational transformation. For whatever reason, and I'm not the only one to think that, people at NRA think the same, there's a lot of hype around it. So if you go this direction, really know where you are going because it's really risky, and we have a lot of experience with it. And the idea behind it and why OT somehow has really kind of problem is that context is a cornerstone of real-time collaboration. This is very, very important concept that operational transformation does not have. And finally, don't transform your operation in your control flow. This makes like this whole mess in operational transformation, which makes everything complex. If we need to summarize CRDD, this is a very good solution to consider. The thing is, it's made to be a very robust distributed system with a massive number of users. We've seen before 2.5 million, on a kind of single document. It's very, very, very good and very robust. It's more made, we've seen this through operation design. The idea is it's very hard actually to elaborate, and it's really hard to design. So usually it's more used like different actually implementation of it you can see in the industry is always server side, because you need to control the cluster infrastructure for security, for example. So it's more something to be done server side. And it's also more server side because as for almost any kind of server program, somehow you need to be to make it so that specifications don't change so much. So if you have non-changing specifications, an infrastructure actually that you can completely handle, in this case, yeah, it might be a good idea to go through CRDD if you can handle the operation design or if you can find operation in the operation portfolio. Okay. For Flip, it's a tiny bit different. So we are not a distributed system, but a central system. And the algorithm is the same thing, very robust. We handle smaller number of users on a single document, but maybe 10,000 or something like that, which is probably just good enough actually for this kind of problem. We are made for more, not server-side, but pro application. So it's typically application when you have an undo. Every time you've got an application with an undo, a pro application, Flip is really made for it. And we can see with CRDD that just making an undo is a very, very complex task. And finally, it's very flexible with system invariants, as we've seen. So even if you've got really quickly changing specification because you are making a new project, for example, it's going to handle it very nicely. So I'm giving back the floor to Frank, and thanks.
Yeah, just come back to answer my initial question. So why do single user applications are still a standard today? As we've seen, it's a long time idea. The reason was the value is high, that's clear, but the price is even higher. The time to market is very long, and more importantly, there is a risk of failure. And today we've talked about the Google waste failure, but there were many, many others, and we can prove it if you want to. So that's clearly a domain where you can spend millions and have nothing working as a result. For example, how many developers have spent years with the diff patch approach to then discover it's a dead end? We think it's a lot, and also we have some example here. And how many developers are working currently on operational transformation? Probably a lot, because that's the first technical theory we find when you look for one on Google. So last year, we've integrated Flip within a market leader. That's a complex application with millions of lines of code, with decades of legacy code, with a team of 50 developers working on it continuously, and probably more for the quality assurance team. And the integration went very beautifully. So that's why we think something had changed, because that will be the first time that a market leader will be turned into a multi-user application with a short time to market and with a generic technology. So we hope that's the beginning of a new era, and that in 10 years we'll have to explain to our kids what a single user application was, because there is no reason for that. Thank you.